So today we're going to learn about binary search. So binary search is about finding an element in a sorted array. So that is important to remember. It is a sorted array. So let's first look at the brute force way of finding an element in a sorted array. Suppose you want to find number 37. The brute force way would be you go through every single item and check if that number is equal to 37. Is this equal to 37? No. This is the index in blue. Is this equal to 37? No. Keep going, keep going, keep going. This is the number at index 5 is 37, so I return 5. So the problem here is, in the brute force way, is that you have to go through every single item. So if your item is not in the array, you have to search the entire array. Also, if the item is towards the end of the array, you have to search the entire array. So this is a little less efficient way. But the fact that it's sorted, we can take advantage of that and make the search faster. Now let's see how we can do that. Now suppose I was looking for number 37 again, but in this way what I do, I divide it in half and directly go to the middle element. Instead of going through every single element from the beginning, directly go to the middle element, which is 45. Now I know this is a sorted array, which means everything to the right, it's sorted ascending. So everything to the right is bigger. So I know 37 cannot be there. So that whole part is eliminated for me, right? So now I only need to search from here to here. Now again, in this sub array, if I do the same thing, where I take the center element, which will be this one. Now from here to here, I pick this one. Again, in this case, this is not 37, but then I know that this is 5. And since this is sorted ascending, everything to the left is smaller. Since 37 is bigger, it has to be on the right side. So basically, now at this point, just looking at two elements, I have eliminated everything to that side, eliminated everything to this side, and I only have to search to these few elements. So this is binary search, where you keep dividing it by half until you reach last one element. And if that element is not the number you're looking for, then you return -1 for not found. So let's look at it. So suppose this, when I start the search, I start with the first element and last. I have an index for the first element and the last element. Now what I do is I go to the middle number, which is this one. So this one is 45, and 45 is bigger than 37. So I know this or anything to the right cannot be the number I'm looking for. So now I move my indexes, my first index and last index. So this is the last index. So since I was here, I move one before that. Since this, including this, all the way to the right, everything's eliminated. So this is my last index. So this is the only subarray left for me to search. Now again, I go to the center element, which is this guy. So 5. Now 5 is not 37. I also know 5 is smaller than 37. So everything to the left is eliminated because it's an ascending array. So everything to the left is smaller, and because 37 is bigger, it can't be on this side. So I go, so this till here, everything's eliminated. So my starting index is this 3, ending index is 5. Now again I look at the middle index, which is 4, 18. 18 is smaller than 37. So anything to the left of 18 in this subarray is eliminated. So I go, my starting index will be +1 because it's to the right, because 37 is bigger. Now this is the last item I'm looking for. Now if this is not the number I'm looking for, at this point I'll return -1. But in this case, 37 is the number I'm looking for, so I'll return 5. So like you see, if I divide it by half, all I had to do was touch 4 elements to find 37. Now if this was here or here or here, it will always be up to 4 in this case for this many elements. So which is much lesser than the total number of elements. So if you're preparing for an interview, they will always ask you about big O of n. So big O is basically the total number of items you have to touch. So compared to the size of the array, or compared to the total number of items. So in this case, the total number of items, so n is total number of items. So our first approach, where we had gone brute force through every single item, in the worst case scenario, so big O is usually the upper bound. So upper bound of how many elements you have to touch. So in the worst case scenario for big O, you have to touch every single item. So we say, in that case, the complexity is big O of n. But in this case, where we're dividing it by half, we don't have to touch every single item, even in worst case. Like if we don't find it, we are still not going to touch 14 items. And if it's towards the end, we are still not going to touch 14 items. So in this case, how it is what we're doing is we keep dividing it by 2 until we are left with one element. So we do n divided by 2, and then we divide it by 2 again, which is basically n by 2 raised to 2. Then we divide it by 2 again, which is n by 2 raised to 3. So we keep dividing by 2 until this becomes 1, the last element, until we have one element left. So which means n by, suppose we have to divide it x times, n by 2 raised to x equal to 1. So x is the number of items you are touching. So this, if you solve mathematically, this is same as 2 raised to x equal to n, which is basically 2, which is basically x is equal to log of n to base 2. So n is the number of items you are touching. So which is the complexity here, log of n to base 2. So in this case, your complexity is your time complexity. Your time complexity is big O of log n, where n is the total number of items, to base 2. So usually in the interview, they will ask you for time complexity and space complexity. So space complexity depends on how you solve it. So if you use recursion, you have the stack frame. So you have to include that in the space complexity. But in this particular case, instead of using recursion, you can just have a while loop where you keep moving the last index and the first index until the first index crosses the last index. So in which case you are not using any extra memory. In which case, if you go with the iterative way, the space complexity would be constant, which is big O of 1. So I have a link to the code at the bottom of the video where I'm using the iterative approach.